so more than we needed to, excess zinc into a copper sulfate solution. We also recorded the change in temperature. Our goal was to find the enthalpy change for this reaction, so the delta H for this. We knew quite a lot about the copper sulfate solution. We presumed that it had a density of 1, which meant that its mass, when we weighed it out, was the same as its volume. For some solutions this isn't true, but for this one it's good enough. We knew quite a lot about the solution, so we call it a standard solution. When this is made, it was made to be 0.400 moles per litre. This is its concentration. So a standard solution we have to know the concentration of. And the symbol for concentration is a little c. We also knew its volume very precisely. Well, not very precisely because we used weighing it to work it out. So probably we only know it to being 53.8, but we'll leave that number there a little bit too precise for now. But we knew its volume. And we have to put the volume into litres. So the reason that I write volume as a capital V is for two reasons. One is my physics background makes me think of little v as velocity or speed. But the other reason is to remind myself to put it into litres, which has got a symbol of capital as a capital symbol as well. Okay, so it's just my little reminder to myself. If I use a capital V for what volume is, I have to remember to turn my volume into litres because it has a capital litre symbol. From this information, I'm able to find out how much the amount of copper sulfate that I have used. Because this is going to be really important for working out my enthalpy change. Because the unit for enthalpy is kilojoules per mole. And mole is our unit for amount. So, without knowing the amount, we can't work out how many kilojoules per mole it was. We only get the energy of the reaction, not the enthalpy. So, our first important thing that we're going to look at today is when we're using a solution, we need to know this relationship. The amount, N, so number of moles, is equal to the concentration times the volume. Alright, so I've got concentration and volume there. Just put my extra little note up there. N is amount in moles. Okay, so N is our amount of stuff in moles. Remembering that 1 mole is that huge silly number, 6 times 10 to the power of 23 particles. Okay, so I need to know how much of this copper sulfate I used, so I know how many kilojoules per mole this reaction absorbs or releases, depending on whether it's endothermic or exothermic. This is where I need you guys to help me out, please, because I don't have a calculator with me. So I need to find out the amount of copper sulfate. So I need some help. So N equals CV, which is 0.0400 times 0.05378. So if I could have someone do that quickly for me, please. You might have to give it to me in standard form, so times 10 to the negative something, or... Be confident. If it's slightly wrong, I'm not too worried for what we're trying to do.
0.02, actually. How do you change this?
Don't need to put it in standard form. I'm happy with this.
0.021512.
Okay, because this has only got 3 significant figures, I'm only going to ask for 3 things, the 2, the 1, and then the rounded off 1. 5. What's the number after the 5? 1. Cool, awesome. Okay, and the unit there is moles, MOL. That's enough precision for us, because there was only 3 in my standard solution, so that's enough for us. Okay, I've now got the amount, so I can find out something per mole, because that's not many, so I'm going to have to use an equation later to work that out. The other thing that we need to know is to do with the temperature change, so I might use red for temperature here. We found that when we did this reaction, now the group whose volume I used there, what was your temperature change, please?
5 degrees.
Positive or negative?
Positive.
positive. So I got hotter by 5 degrees Celsius. Okay, so our temperature change is 5 degrees Celsius. We also know that the mass of copper sulfate that we used, okay, so we know its volume and we know its mass, they're the same. So 53.78 grams. This is because it's an aqueous solution, so its density is pretty close to 1 gram per mil. So if I know my exact volume, I also know my exact mass. This is why we record it in mils, so that it's got a meaningful unit for this next step. We also know it was an aqueous solution, so the specific heat capacity, which has got two possible symbols, S or C. To keep it different to this one, I'm going to call it SH2O, specific heat capacity of water, is 4.2 joules per degree Celsius per gram. You would be given this number. You would be given this number. So don't try to memorise it. Sometimes they put 4.18. Okay, so what we need to do is go, well, what do we do with that information? And this is where I need to write another equation for you. This is about heat energy because it's something getting hotter or getting colder. Q is heat energy. It is M times the specific heat capacity of whatever it is that's changing temperature, in this case water, times the change in temperature, and it gives us the answer in joules. So Q is heat energy in joules. Alright, so just to be aware of that, so I can't underline anything to help you with that. Joules being J, not kJ. Kilojoules is kJ. So we're going to plug those numbers in. And we're going to find what our Q value is. I'm going to need some help again with this, please, because those numbers are too complicated. So taking this information here, 5, 53.78 and 4.2, I need to know my Q value, please. So 5, sorry, let's do it in the right order. 53.78 times 4.2 times positive 5.
1,129.38.
Okay, so 1,129. So again, let's just go to 3 significant figures to be consistent with what we had there. So 1130. And that's joules. Now, we should know the difference between kilo and milli and all those sorts of things. We want it in kilojoules. So I'm going to change it into kilojoules. If it's 1,130 joules, how many kilojoules is it? 1.13 kilojoules. Awesome. Now, when I work out enthalpy change, so I'm going to go to green, so it's the same as our equation. When I look at enthalpy change, I need to know how many kilojoules per mole. That was the number of kilojoules released, because it got hotter, per 0.0215 moles. So how do I make it so that it's per mole? What I need to do is basically divide both of those by 0.0215 to make them 1. Make this one 1 and this per mole. So my last equation for you, sorry, I should have circled that one. My last one for you is that my enthalpy change is the amount of energy released or absorbed. I do the negative of it because if something got hotter, it means the enthalpy of the chemicals got lower. If it got colder, it meant the enthalpy of the products was higher. So I negative the Q value I've got and divide it by my number of moles. So that's my last really important equation. So I go negative 1.13. Hoping this is fitting on the video. Negative 1.13 divided by 0.0215.
Negative 52.55.
Negative, what was it?
Negative 52.
52, sorry.
0.558.
So 52.6 kilojoules per mole. Now if I knew my bond enthalpies or bond energies for these things here, I could then calculate it. We're not going to try and compare and contrast. What we would find is if we looked this up on the internet, is that this number is probably not actually that accurate. Even if it was rounded off to one significant figure at negative 50 kilojoules per mole. We'd find it's quite inaccurate. And the reason is we had a thing called an open system. We did this in a polystyrene cup. There was going to be some heat lost to the environment that we couldn't record with our thermometer and that sort of thing. We also didn't, this could have changed over between when it was made and when we used it because it was not necessarily kept in a closed bottle and that sort of thing. So sometimes our calculated values are not as precise as we need them to be, which is why we often use bond energies to work out these values. Any questions or comments?
Wait, so is the Q always negative?
No, if it was a negative temperature change, you'd get a negative Q. Negative of a negative is positive, isn't it?
Yeah.
So whatever value you get here, positive or negative, take the negative of that when you're working out delta H. Delta H is what's happening to the chemicals. Q is what's happening to the solution that it's dissolved in. Very good question, thank you. So is that quite clear to everyone? You've got Q is what's happening to the surroundings, in this case the water. Delta H is what's happening to the chemicals in the equation. Alright, so one will go up and one will go down, and they should be by the same amount, because that's conservation of energy. Alright.